Hello everyone, my name is Hunor and in this tutorial we are going to cover how to create a clone of the mobile game Crossy Road with Three.js. The goal of this game is to move a character through an endless path of static and moving obstacles. We have to go around the trees and avoid getting hit by a car or a truck. There's a lot to cover in this tutorial. We are going to start with setting up the scene, the camera and the lights. Then we learn how to draw the player and the map with the trees, the cars and the trucks. We cover how to animate the vehicles and we add event handlers to move the player through the map. Finally, we add hit detection between the cars and the player. There's a lot to cover, so let's get started. In this chapter, we are going to set up the drawing canvas, the camera, the lights, and we are going to render a box that will represent our player. To initialize the project, I recommend using Vite. With Vite, you can just go to your terminal and type npm create Vite, and it will create an initial project for you. When generating the project, select Vanilla because we're not going to use any front-end framework for this project. Then navigate to the project folder that Vite just created for you and install Three.js with npm install 3. Finally, you can go to the terminal, type npm run dev to start a development server. This way you can see live the result of your coding in the browser. Now let's look into this project. The entry point of this project is the index.html file in the root folder. Here let's replace the div element with a canvas element with the ID game. This will be the drawing canvas that Three.js will use to render the scene. This file also has a script tag that points to the main JavaScript file. Let's look into that next. This file is the root of our game. Let's replace the content of this file. Here we define a Three.js scene that will contain all the 3D elements, including the player that we are going to define soon. The scene also includes a camera that we use together with the renderer to render a static frame of the scene. We define these in the next steps. Before we move forward, let's get rid of a couple of files that Vite created for us, but we don't actually need. We can remove the javascript.svg file and the counter.js files from the source folder. We can also delete most of the things in the CSS file. The only thing that we need for now is to remove the default margin around the body element and to make sure that the body element is filling the whole screen. Now let's start adding the necessary objects to render the first scene. Let's create a new folder called Components. This folder will mainly contain files that expose Three.js objects that we can add to the scene. Some files will also expose a state or additional functions that modify the exposed Three.js object or the state. Then let's create a file for the renderer. The renderer function creates a Three.js renderer that we can use to render the scene. I'm using capital letters for functions that return a Three.js object. In this function, we get the canvas element we just defined in HTML and set it as the drawing context. We also set a couple more parameters. For instance, we make the background of the 3D scene transparent with the alpha flag. We set the pixel ratio, and we set the size of the canvas to fill the entire screen. Now let's look into the different camera and light options. There are two main camera options, the perspective camera, as you see it on the left, and the orthographic camera, as you see it on the right. The perspective camera is the default camera in Three.js. It's the most common camera type across all video games. It's creating a perspective projection, which makes things further away appear smaller and things right in front of the camera appear bigger. The orthographic camera, on the other hand, creates parallel projections, which means that objects have the same size regardless of their distance from the camera. We are going to use an orthographic camera as it's giving our game a more arcade, retro, boxy look. Now let's talk about the coordinate system, placing the camera and the direction of the camera. In Three.js, we are placing the 3D objects along the X, Y, and Z axis. We define the coordinate system in a way where the ground is on the XY plane. So the player can move left and right along the x-axis, forward and backward along the y-axis, and when the player is jumping, it will go up along the z-axis. We are going to place the camera in this coordinate system to the right along the x-axis, behind the player along the y-axis, and above the ground. Then the camera will look back at the origin of the coordinate system to the 0, 0, 0 coordinate, where the player will be placed initially. With all this theory, let's define our camera. We create a new file for the camera. In this file, we export the camera function that will return an orthographic camera that we will use to render the scene. To define a camera, we need to define a camera frustum. We will define how to project the 3D elements to the screen. In case of an orthographic camera, we define a box. Everything on the scene within this box will be projected onto the screen, and everything outside of it will be off-screen. Let's look at the demo here. Here the green dot represents the camera position, and the line going to the player shows that it's looking towards the player. The gray box shows the camera frustum. The green rectangle shows the intersection of the box with the ground to make it easier to see which part of the scene is part of the camera frustum. So basically what we see here is that we are looking at the scene from this direction, and everything that's outside of this box will be off-screen. Things that are to the left from the box are going to be to the left from the screen, and so on. We define this frustum by defining the distances from the camera position to each side of the box. We define the left, right, top, and bottom values, and we also have a near and far value. The near value basically says that if something is too close to the camera, we won't show it, and if something is too far away, we won't show it either. These are for performance reasons. In this function, we set up the camera frustum to fill the browser window, and the width or height will be 300 units, depending on the aspect ratio. Basically, the smaller value between width and height will be 300 units, and the other one will fill the remaining space. If the width is larger than the height, then the height is 300 units. If the height is larger, then the width is 300 units. Then we also set the camera's position. We move the camera to the right along the x-axis by 300 units, then behind the player along the y-axis with minus 300 units, and finally above the ground. We also look back to the origin of the coordinate system, to the 0, 0, 0 coordinate, where the player is positioned initially. And then we also have to set which axis is pointing upwards. Here we set that the z-axis is pointing upwards. After setting up the camera, let's set up the lights. There are many types of lights in Three.js. Here we are going to use an ambient light and a directional light. You can see the result of ambient light only on the left side. The ambient light brightens the entire scene. It doesn't have a specific position or direction. You can think of it as the light on a cloudy day when it's bright but there are no shadows. The ambient light is used to simulate indirect light. The downside of using an ambient light is that as a result, every side of our objects are equally bright. Every side of our boxes will have the same color, so we don't see the edges between them. Now let's look at the directional light that you can see on the right. A directional light has a position and a target. It shines light in a specific direction with parallel light rays. Even though it has a position, you can rather think of it as the sun that is shining from very far away. The position here is more to define the direction of the light, but then all the other light rays are also parallel with this light ray. So you can think of it like the sun. The downside of using directional light is that parts of the objects that don't receive light directly will be completely black. So if we turn around the scene, then we see that this part of the scene is just black. That's why we're combining an ambient light to have a base brightness all around the scene, and then we add a directional light to illuminate specific sides of our objects with a brighter color. After seeing how the lights look like, let's add an ambient and directional light to the scene in our main file. We also position the directional light to the left along the x-axis, behind the player along the y-axis, and above the ground. The target of the directional light by default is going to be the 0, 0, 0 coordinate. We don't have to set that. We set up a lot of things already. We have the camera, we have the lights, we have the renderer, but we still don't have anything visible on the screen. So let's add a simple box that will represent the player. We already added the player to the scene in the main file. So let's see how to define this player. In this file, we write a function that creates a 3D object and export a property containing the player instance. The player is singleton. We only have one player object in the whole game, and every other file can access it through this export. Initially, the player will be a simple box. To draw a 3D object, we define a geometry and a material. The geometry defines the object's shape, and the material defines its appearance. Here we use a box geometry to define a box. A box geometry takes 3 arguments: the width, depth, and height of the box along the x, y, and z axis. For the material, we have different options. The main difference between them is how do they react to light, if they react to light at all. Here we are using Mesh Lambert material, which is a simple material that responds to light. We set the color property to white here. Then we wrap the geometry and the material into a mesh. A mesh is something that we can add to the scene. We can also position this mesh by setting its x, y, and z positions. In the case of a box, these set the center position. So here, by setting the z position of this box, we elevate the box above the ground by half its height, so as a result, the bottom of the box will be standing on the ground. With this, now you should finally see a 3D object on the scene. Now let's add all the other objects to the scene. In this chapter, we are defining the map. The map will consist of multiple rows, each described by metadata. Each row can be a forest, a car, or a truck lane. We're going to go through each type and define the 3D objects that represent them. The map can be broken down into rows, and each row can be broken down into multiple tiles. The player will move from tile to tile. Trees are also placed on a distinct tile. Cars and trucks, on the other hand, do not relate to tiles. They move freely through the lane. We define a file for the constants. Here we define how many tiles each row has. In this case, we have 17 tiles per row, going from -8 to +8. The player will start in the middle at tile 0. First, let's add the starting row. We define a couple of components that we use to render the map, and we render the initial row. Let's create a new component called map. This file will expose the map's metadata, the 3D objects representing the map, and functions to extend and reset the map. Let's export a group called map. This container will contain all the 3D objects for each row. Soon we will add this group to the scene. We also export the initialize map function, which sets the map's content. Later we will extend this function to generate the 3D objects based on the metadata and use it to reset the map. For now, let's just call the grass function, which will return another Three.js group. We call the grass function with the row index, so the grass component will position itself based on this row index. Then we add the return group to the map. Now let's define the grass component. So far the map was just a container for all the rows, and now we're defining the content. The grass function returns the foundation and container of the forest rows, and it is also used for the starting row. It returns a group that contains a flat, wide, green box. The dimensions of this box are determined by the constants tiles size and tiles per row. It also has a bit of a height, so it sticks out comparing to the road, which will be completely flat. The grass can serve as a container for the trees in the row. That's why we've wrapped the green box into a group so that later we can also add children to this group. We position the group along the y-axis based on the row index that we received from the map component. For the initial lane, this is obviously 0, but as we're going to have multiple lanes, we need to place them according to this position. Now that we have the map container and now that we have the grass component, we can finally add the map to the scene in the main file. Since the map is initially an empty group, we also have to call the initializeMap function to render its content. So let's also define an initializeGame function which will set up the map's content. Later we are going to extend this function and also use it to reset the game. Make sure to call this function before we render the scene, otherwise an empty map will be rendered. Now that we have an empty forest, let's add another row that will contain trees. We define the metadata for the map and we render the rows based on this metadata. Back in the map component, let's define the map's metadata. The metadata is an array of objects that contain information about each row. Each row will contain a type that will determine the kind of the row and the rest of the properties depending on the row type. For now, let's hardcode these values. Later, we are going to generate them dynamically. The metadata for a forest has the type forest, and it also has a list of trees. Each tree has a tile index, which will represent on which tile the tree is standing on. In this case, we have 17 tiles per row, going from -8 to +8. The trees also have a height, which will actually be the height of the crown. To render the rows, we call the addRows function in the initializeMap function. This function generates 3D objects based on the metadata and adds them to the map container. The addRows function loops over the metadata and creates 3D objects for each row based on the row type. For the forest type, it calls the grass function again, which will return a Three.js group. We call this grass function with the row index, so the grass function can position itself along the y-axis. The row index is off by 1 compared to the array index because the first item in the metadata will become the second row right after the starting row, which is not part of the metadata. Forest rows also have trees. For each item in the trees array, we render a tree. The tree function will return a 3D object representing the tree. We pass on to this function the tile index that we will use to position the tree within the row and the height. We add the trees to the group the grass function returned. Then we add the whole group returned by the grass function to the map. Since we already added the map to the scene, the forest will appear on the screen. But first we need to define how to render a tree. We are going to represent a tree by 2 boxes. We are going to have a box for the trunk and one for the crown. These are both simple boxes just like we had before with the player and also in the grass component. The trunk is placed on top of the ground. We lift it along the z-axis by half of its height, and the crown is placed on top of the trunk. The crown's height is also based on the height property. These 2 meshes are wrapped together into a group, and then we position this group along the x-axis based on the tile index property. Now let's add another row type. Let's add car lanes. Adding car lanes will follow a similar structure. We define metadata for the lanes, including the vehicles, and then we map them into 3D objects. In the map component, in the metadata, let's replace the first row with a car lane. The car lane will contain a single red car moving to the left. We have a direction property, which is a Boolean flag. If this is true, that means the cars are moving to the right in the lane, and if it's false, then the vehicles are moving to the left. We also have a speed property, which is defining how many units each vehicle takes in every second. And finally, we have an array of vehicles. Each car will have an initial tile index, which will only represent the initial position because later the cars are going to move. And each card will also have a color property, which is a hexadecimal color value. Now to render this lane type, we have to extend our addRows function to support car lanes. We add another if block that is very similar to rendering a forest. In case of a car type, we call the road function, which will also return a Three.js group. We also call this function with the row index to position the group according to the lane. Then for each item in the vehicles array, we create a 3D object representing the car with the car function. We add the cars to the group returned by the road function, and we add the whole group to the map. To the car function, we also pass on the initial tile index that we will use to position the car within the row, the direction, and the color. The road and the car functions are new here, so let's look at them next. The road function returns the foundation and container of the car and truck lanes. It returns a group that contains a gray plane. Similar to the grass function, the size of the plane is also determined by the constants tile size and tiles per row. Unlike the grass function though, it doesn't have any height. It's completely flat. The road will also serve as a container for the cars and trucks in the row. So that's why we wrap the plane into a group so that later we can add children to it. Now let's look at the car. The car function returns a very simple 3D car model. It contains a box for the body and a smaller box for the top part. We also have two wheel meshes for the wheels. We group all these elements together, position them based on the initial tile index property, and turn them based on the direction property. If the car goes to the left, we rotate it by 180 degrees. When we are setting rotation values in Three.js, we have to set them in radians. So that's why we set it to met.pi, which is equivalent with 180 degrees. Finally, we have to define the wheel. To continue our boxy theme, the wheel function also returns a simple box with a dark color. Because we never see the cars from under, we don't need to separate the wheels into left and right. We can just use one long box for the front wheels and another one for the back wheels. Now, if we want to have truck lanes as well, then we essentially follow the same structure. We can define the metadata just like for the car lanes, except now we have a type truck, and then we also have direction, speed, tile index for the vehicles, and colors for the vehicles. I'm not going to go through this, but it's essentially the same logic. We are mapping over the metadata to 3D objects, which this time we'll use the truck object instead of the car object, and the trucks are also built up from 3D boxes. Now we can render a map with several rows based on the metadata. For aesthetic reasons, we can also add a couple empty rows before the player. In the initialize map function, instead of adding one single grass row, we can add multiple ones with a loop that will fill the empty space before the player. Before we move on with the game logic, first let's add shadows. In this chapter, we define the shadow camera and we ensure that the object on the scene can cast and receive shadows. To enable shadows in the scene, first we have to enable shadow maps in the renderer. This is one flag that we have to set to true. Then we are going to update our directional light to cast shadows. The directional light will have many more properties, so let's create a new file specifically for the directional light. First, we need to set the light cast shadow property to enable shadow casting. We also need to set the map size for the shadows to set the resolution of the shadow map. Higher values result in sharper shadows but might be less performant. Then we need to set a shadow camera. A shadow camera renders the scene from the perspective of the light to calculate shadows. Here we need to define a camera frustum again. In the case of directional light, the shadow camera is an orthographic camera and its frustum is a box. Shadows are only calculated within this box. In this demo now, the green dot still represents the main camera that points towards the player. Then we define a shadow camera frustum like when we set up the main camera. Here the red dot represents the position of the directional light, and the line going to the player represents its direction. All the light rays are parallel with this vector. The bigger gray box around the scene represents the shadow camera frustum. The near, far, left, right, top and bottom values represent how far each side of the frustum box is from the camera position along the different axes from the camera's perspective. The red rectangle shows what part of the ground is part of the shadow camera. As the red rectangle covers more than the green rectangle, representing the visible area, every object in the scene should be able to cast and receive shadows. Now that we have defined the directional light in its own file, let's replace the original directional light in the main file with a call to this new function. To enable shadows in the scene, we have to set for each mesh that we are using if they can cast shadows and if they can receive shadows. First, let's set for the grass and road components that they can both receive shadows. You can also set that they cast shadow, but because they are on the ground, they wouldn't cast shadow to anything below them. So let's just have the receive shadow property set to true. Then for the player, the trees and cars and trucks, we need to set both the cast shadow and the receive shadow properties for every mesh that they consist of. So in case of the player, we only have one mesh. We set to the body that it can cast and receive shadows. For the tree, we actually have two different meshes, so we can set that the crown can cast shadows and the trunk can cast shadows, and so on. We do this, of course, with the cars and the trucks. And then finally, we have a scene where the player, the trees, the cars, and the trucks have a shadow. Alright, let's move on with animating the cars and the trucks in their lanes according to their speed and direction. To move the vehicles, first we need to be able to access them. So far we have added them to the scene, and theoretically we could traverse the scene and figure out which object represents a vehicle, but it's much easier to collect their references in our metadata and access them through these references. Let's modify the add rows function. After generating a car or a truck, we not only add them to the container group, but also save their reference together with their metadata. After this, we can go through the metadata and access each vehicle in the scene. Next, let's go to the main file and let's define an animate function that will be called on every animation frame. For now, we only call the animate vehicles function in it, which we are going to define next. Later, we also extend this function with logic to animate the player and with hit detection. We also move the renderer's render call here to re-render the scene on every animation loop. To call this function on every frame, we pass it on to the renderer's setAnimationLoop function. This is kind of like request animation frame in plain JavaScript, except that it's calling itself at the end of the function, so we don't have to call itself again. Now let's implement the animate vehicles function. As this function is part of the animate function, this function is called on every animation frame. Here we use a Three.js clock to calculate how much time passed between the animation frames. Then we loop over the metadata, take every vehicle from every car or truck lane, and move them along the x-axis based on their speed, direction, and the time passed. If the vehicle reached the end of the lane, we respawn it at the other end, depending on their direction. This way we have an infinite loop in which cars go from left to right or right to left, depending on their direction, and once they reach the end of the lane, they start over from the beginning. With this function, we should have a scene where all the cars and all the trucks are moving in their lanes. Now let's move on to animating the player. Moving the player on the map is a bit more complex than moving the vehicles. The player can move in all directions, it can bump into trees, get hit by cars, and it shouldn't be moved outside the map. In this chapter, we are focusing on two parts: collecting user inputs and executing the movement commands. Player movement is not instant. We need to collect the movement commands into a queue and execute them one by one. We are going to collect user inputs and put them into a queue. We collect both click events from the control buttons on the screen and from keyboard events. To track the movement commands, let's extend the player component with state. We keep track of the player's position and the movement queue. The player starts at the middle of the first row, and the moves queue is initially empty. We will also export two functions. The moves queue adds the movement command to the end of the moves queue, and the step completed function removes the first movement command from the queue and updates the player's position accordingly. Now let's add some buttons to the screen. So let's go back to our HTML file and add a few buttons. We add 4 buttons to move the player forward, left, backward, and right. We wrap these buttons into 2 divs. The outer div will place the controls to the bottom of the screen, and the inner div will have a grid layout to align these buttons nicely. This is how the CSS looks like. I'm not going to go through the CSS in detail. We basically use absolute positioning to place the controls at the bottom of the screen, and then each button is displayed in a grid layout where the forward button spans to all 3 columns to make it wider. Next, we can add event listeners to the buttons and also for keyboard events to listen to the arrow keys. They all call the player's queueMove function that we just defined for the player with the corresponding direction. Note that we are also preventing the default behavior of the arrow keys to avoid scrolling the page. Now, after defining the event listeners, we also have to import them into the main file so that they actually work. Now, so far we were collecting user inputs, and we put each command into the moves queue array in the player component. Now it's time to execute these commands one by one and animate the player. Let's create a new function called animate player. Its main goal is to take each move command from the moves queue one by one, calculate the player's progress towards executing the step, and position the player accordingly. This function animates the player frame by frame. It will also be part of the animate function. We also use a separate move clock that measures each step individually. We pass on false to the clock constructor so it doesn't start automatically. The clock only starts at the beginning of a step. At each animation frame, first we check if there are any more steps to take, and if there are and we don't currently process a step, then we can start the clock. Once the clock is ticking, we animate the player from tile to tile with each step. We use the move clock to calculate the progress between the 2 tiles. The progress indicator can be a number between 0 and 1. 0 means that the player is still at the beginning of the step, and 1 means that it arrived to its new position. At each animation frame, we call the setPosition and setRotation functions to set the player according to the progress. Once we finish a step, we call the stepCompleted function to update the player's position and stop the clock. If there are any more move commands in the moves queue, the clock will restart in the following animation frame. Now that we know how to calculate the progress for each step, let's look into how to set the player's position and rotation based on the progress. The player will jump from tile to tile. Let's break this down into 2 parts, the horizontal and the vertical components of the movement. The player moves from the current tile to the next tile in the direction of the move command. We calculate the player's start and end position based on the current tile and the direction of the move command. Then we use linear interpolation with a utility function that Three.js is providing for us. This will interpolate between the start and end position based on the progress. For the vertical component, we use a sine function to make it look like jumping. We are basically mapping the progress to the first part of a sine wave. This is how a sine wave looks like. It goes from 0 to 2 pi's. So if you multiply the progress value, which is going from 0 to 1, with pi, then the progress will map into the first half of this sine wave. The sine function then will give us a value between 0 and 1. To make this higher, to make the jump look higher, we can multiply this with a value. So in this case, we are multiplying the result of the sine function with 8. So as a result, the player will have a jump where the maximum height of the jump will be 8 units. Now this was the positioning part. The player is also turning into the direction of the move command. Here we use linear interpolation again to calculate the player's rotation based on the progress. We figure out what should be the end rotation of the player based on the move, and then we turn the player into that direction. Now that we defined the animate player function, let's add it to the animate loop. If we did everything right, the player should be able to move around the game board. The player should move forward, backward, left and right, and rotate accordingly. Now, if you start moving around, the player is already moving, that's good, but you will notice that the player will sink halfway into the ground after the first step. This is because the animation assumes that the player's resting position is at 0. We position the boxes by their center, and this box should be above the ground by half of its size and not at 0. To fix this, let's wrap the player into a group. The group's resting position will be at 0, and then the box inside of it will be elevated relative to the group by half of the box's height. So as a result, if the animation function is resetting its Z position to 0, we are going to have a good position. Now that we can rotate the player into a direction, it's also handy to have a visual indicator of the player's direction. Let's add a new mesh on top of the player's body that will serve as a little yellow cap. If we did everything right, the player should be able to move around the game board. The player should move forward, backward, left and right, and rotate accordingly. However, we haven't added any hit detection so far. The player can move through trees, vehicles, and even get off the game board. Let's fix these in the next chapters. In this chapter, we are going to make sure that the player can't take a position that is invalid. We will check if a move is valid by calculating where it would take the player. If the player would end up in a position outside of the map or on a tile occupied by a tree, we will ignore that move command. First, we need to calculate where the player would end up if they made a move. Whenever we add a new move to the queue, we need to calculate where the player would end up if they made all the moves in the queue and take the current move command. We create a utility function that takes the player's current position and an array of moves and returns the player's final position. We will use this information to check if the player can make that move. For instance, if the player's current position is 0, 0, staying at the first row in the middle, and the moves are forward and left, then the final position will be row 1, tile -1. Now that we have this utility function to calculate where the player will end up after taking a move, let's create another utility function to calculate whether the player would end up in a position that is valid or invalid. In this function, we use the calculate final position function that we just created. Then we check if the player would end up outside the map or on a tile occupied by a tree. If the move is invalid, we return false. First, we check if the final position is before the starting row, or if the tile number is outside the range of the tiles. Then we check the metadata of the row the player will end up in. Here the index is off by 1 because the row metadata doesn't include the starting row. Now, if we end up in a forest row, we check whether the tile we move to is occupied by a tree. If any of this is true, we return false. Finally, let's extend the player's queueMove function with the ends-up-in-valid-position function to check if a move is valid. If the ends-up-in-valid-position function returns false, that means that we cannot take this step. In this case, we return early from the function before the move would be added to the move's queue array. So basically, we are ignoring the move. This way, as you can see, you can move around the map, but you can never move before the first row, and you can't go too far to the left or too far to the right, and you can also not go through a tree anymore. Now we can move around with the player on the map, but the camera still points to the starting position. Let's follow the player with the camera. In this chapter, we attach the player to the camera so they move together. We also adjust how the shadow camera is casting shadows. Originally, we attached the camera to the scene in the main file. This way it has a static position. Instead of that, we want to move it together with the player. We could adjust its position at every animation frame just like we did with the player, but it's much easier if we add it directly to the player. So this way, they are going to move together. Once we attach the camera to the player, some strange things are happening. The camera is moving together with the player now, but it's also turning whenever the player turns, and it's also moving up and down whenever the player is jumping. This is not exactly what we wanted. We want the camera to follow the player, but we want it to stay in level and not jump or turn. To ensure the camera follows the player but doesn't turn or jump with it, we wrap the player object into another group. This new group will be a container that moves horizontally on the map but doesn't jump or turn. We add the camera to this group. Then the original group containing the player objects won't move horizontally anymore, but keep turning and jumping as before. Let's adjust the player animation to use this new structure. In the utility functions of the animate player function, we need to adjust how we set the player's position and rotation to work with the new structure. When moving the player along the x and y axis, we need to move the outer group, but when the player turns or jumps, we need to adjust the inner group. These functions receive the reference to the outer group. We set the x and y positions as before. When we set the position or rotation along the z-axis, we set it to the inner group though. We can access the inner group by accessing the first child of the player object. Now the camera is moving together with the player in a nice way. But as the player moves further away, another strange thing will happen. At one point, the objects will no longer have a shadow anymore. If we zoom out even more and add the helper box to show the shadow camera's frustum, we can see that some parts of the game are now outside of it. Here the gray box shows the shadow camera's frustum, and the red rectangle represents its intersection with the ground. So you can see that the beginning of the map is part of the shadow camera frustum, but as we progress forward, at one point we just run out of it. We need to attach the directional light to the player as well. We can attach the directional light to the player in the main file just like we did with the camera. Now, if we do that, we are still not exactly finished with this. If we are moving around, at one point the shadows are going to behave a bit strangely. This is because directional lights shine from their position towards a target, and by default the target is the origin, the 0, 0, 0 coordinate. This was fine when the light was attached to the scene, but now that it's attached to the player, we also need to adjust the target. Otherwise, the light and the shadows will keep changing direction. So let's set the directional light's target in the main file to point to the player. So far we have rendered the map based on static metadata. Now it's time to generate the map randomly and dynamically expand the level as the player moves forward. In this chapter, we add utility functions that generate metadata and use them to render the map. So let's create a new utility function to generate metadata. In this, we export the generate rows function, which will return the metadata for X amount of rows. The generate rows function will call the generate row function, which generates the metadata for one single row. It randomly selects a row type, car, truck, or forest. It uses a new helper function, random element, to pick a random element from an array. Now let's look into the functions that generate the metadata for each row type. Let's continue the same file and add a generate forest metadata function, which will return the metadata for a forest row. To generate metadata for a forest, we need to generate an object with a type property set to forest and an array of trees. Each tree has a tile index and a height. We generate 4 trees in a forest. We pick a random tile index for each based on the available range. We use a utility function from Three.js to pick a random integer between the minimum and maximum tile index. To avoid overlapping trees, we keep track of the occupied tiles in the occupied tiles set. If the generated position is already occupied, we keep generating a new tile index until we find one that is free. So let's say we pick tile -3 for the first tree. We mark this tile as occupied, so the following trees won't be placed here. We also pick a random height for each tree from an array. Of course, you can also have completely random values for the tree height, but I find it nicer if we have a distinct set of tree types. Now, to generate a car lane, we also have a very similar function. Car lanes also have a direction and the speed property. The direction is a Boolean value determining whether the car is moving to the left or to the right. And the speed property tells us how much distance each car moves in 1 second. We pick a random value for both properties with our utility function. Then we need to generate an array of vehicles with the initial tile index and color properties. We generate 3 cars in a lane. The logic here is similar to before when we were generating a forest, except that cars are longer. We need to mark 3 tiles as occupied for each vehicle to avoid overlapping cars. Then finally, generating metadata for the truck is again almost the same as generating metadata for a car, except trucks are even longer, so we mark more tiles as occupied as before, and the rest is pretty much the same. Now let's use these metadata generators in our map component. First, now that we are not going to use a hard-coded metadata, first let's make sure that our metadata array is empty. Then let's return to the addRows function. This function will now generate the map's metadata and also add the 3D objects based on it to the map. We call the previously defined generateRows functions to generate metadata for 20 rows. We push the result into the metadata so other parts of the game can access it, for instance, the previously defined hit detection for the trees, and then we generate 3D objects and add them to the map as we did before. Now that we can generate rows dynamically, let's add new rows as the player moves forward. Let's change the addRows function again to support 2 scenarios, generating initial set of rows and generating rows that extend the current map. We need to change 2 things here. When adding rows to the map, we process only the new metadata that represents the rows to be added. The old rows are still part of the scene. And before we push the new rows into the metadata, we got how many rows we already have there. This will be the start index variable that we can use to calculate the row index. As this function can extend the existing map, we need to know from which position we can add the new rows. So we will add the new rows after the previous ones. Now let's add logic to extend the map as the player is moving forward. Once the player has completed a step, the step completed function gets called. This is a good place to check if the player is running out of the current map. We check if the player is less than 10 rows away from the end of the current map. And if so, we call the addRows function to add new rows, which will add 20 new rows now. As a result, we have an infinite amount of rows. As the player moves forward, more and more rows are added to the map. Now that we can move forward through infinite rows of obstacles, let's add a score indicator to keep track of how many rows we have crossed. Let's add a new div element with the ID score to our HTML file. This simple div contains the number 0 as the initial value. We will update this value as the player is progressing. We also style the score indicator. We position the score in the top left corner of the screen with absolute positioning. We also load a font from Google Fonts that is matching our theme, and we set the font as the default font family for the whole application. Now let's get back to the player component again, and again in the step completed function, this is a good place to update our score. We get a reference to the score element by ID, then we set its inner text value to the current row. This is not the most refined solution, so feel free to change the update so it only gets updated if the new value is higher than the previous one, but it works for now. Now with having the score indicator in place, the final piece is the hit detection. In this chapter, we implement hit detection and add a result screen. We check if the player gets hit by a vehicle, and if so, we show the final score and add logic to reset the game. Once the player gets hit by a vehicle, the game is over. We show a result screen with the final score and the button to restart the game. Let's extend our HTML file with the following code. This will be a simple div that shows game over. It has the final score indicator, which is just a span, and the button with an ID retry. We also set some styling for this pop-up. We style the result as centered with a white background and the red button to restart the game. By default, this result screen is hidden. Let's define another function to define hit detection. We check if the player intersects with any of the vehicle. If they do, we show the result screen. We check which row the player is currently in. The index is off by 1 because the row metadata does not include the starting row. If the player is in the starting row, we get undefined. We ignore that case. If the player is in a car or truck lane, we loop over the vehicles in the row and check if they intersect with the player. We create bounding boxes for the player and the vehicle to check for an intersection. This might be an overkill as the shape of our object is known, but it's a nice generic way to handle hit detection. If the bounding boxes intersect, we set the result pop-up to visible and set the final score in the appropriate field. We call this function in the animate function that will run it on every frame. Once the player is hit by a vehicle, now the result screen should show up. Here we have a button to restart the game. Let's add an event handler to this button in the main file. On the click event, we call the initialize game function that we used before to render the initial map. Now this function will serve two purposes: render the initial map and reset the game. Let's extend it accordingly. We already call it to initialize the map. We are going to extend its logic to reset the map too. However, we don't have any logic to reset the player. Let's import a new function from the player and call it here. We will define this function in the next step. Finally, we need to reset the UI elements. We set the score indicator back to 0 and hide the result screen. Now let's look into how to reset the player and the map. To reset the player, let's export an initialize player function from the player component. This function resets the metadata and the player object's position and rotation in the scene. It sets back the current row and current type positions to 0, it clears the move skew, and it will also change the position of the player object to 0, 0, 0. Finally, to reset the map, we extend the initialize map method to reset the metadata and remove all existing rows from the map before it generates a new set of rows. With this, you should have a fully functioning game. Congratulations, you reached the end of this tutorial. I hope you had great fun creating this game. This game, of course, is far from perfect. You can now extend this game by adding new features, obstacles, and new level design. I'm also very happy to share that I just created a new website that is completely free, where you can find this whole tutorial written down with all the code snippets, and you can try out the interactive demos as you're going through the game. So check out javascriptgametutorials.com, where you can find this tutorial, the upcoming tutorial from next week, and hopefully more game tutorials in the future. So check out javascriptgametutorials.com. So what's next? Now that we covered this game with plain vanilla JavaScript and Three.js, I'm going to cover the same game the next week with React Tree Fiber and React. We're going to recreate the same game with the same features, and the structure is going to be similar to this one. But of course, we're using React Tree Fiber, so a bunch of things are going to be different. If you also want to learn how to use React Tree Fiber, check out that video the next week. See you in the next one.